Hi, good afternoon to all of you. Welcome to Vidyalakshmi YouTube channel. This is Naresh Study Chemistry faculty from Vidyalakshmi School. And in last video, we discussed about what is the meaning of coordination compounds and what is the importance of that studying of the coordination compounds and who explained first the formation of the coordination compounds. That is Werner theory, right? So these concepts we discussed in last video. So in today's video, let us discuss about some basic definitions of the coordination compounds. Okay. So before going to start about the coordination compounds, we have to know some terms which belongs to these coordination compounds only. So those terms in this class we will discuss, and next video we will see about the IUPAC nomenclature of these coordination compounds. Okay. So shall we start? Yes. So let us go to some basic concepts of coordination compounds. Okay. So the first term is coordination entity. The first term is coordination entity. So what is the meaning of coordination entity? Means constitute a central metal atom or ion bonded to a fixed number of ions or molecules, right? So that means, for example, if I take this complex compound, in this complex compound, here cobalt is a metal atom which is bonded to the 3 chlorine atoms, that is 3 chloride ions and 3 ammonia molecules. Some fixed number, when cobalt is going to form this complex compound, on that 3 chloride ions and 3 ammonia molecules should bind to the cobalt. So fixed number of chlorine and fixed number of ammonia molecules bind. So that number of fixed number of ions or molecules which are bounded to the central metal atom constituently we are calling as coordination entity. Okay, that constituent together we call as coordination entity. Clear? Now, in that coordination entity, which one is taking the electron or which one is going to bind with the negative ions or neutral molecules, that we call as central metal atom or ion. Central metal atom or ion. In this example, what we discussed, here 3 chloride ions and 3 ammonia molecules are going to bind with cobalt, right? Okay. So here, which one is taking the electrons to form this complex compound means cobalt. So cobalt take the electron pairs from the negative ions or neutral molecules and forms a bond. Okay, that atom we are calling as central atom or ion. Usually in complex compounds or coordination compounds, the central metal atom or ion is transition metal. Transition metal, it acts as a central atom or ion. To the empty orbitals of the transition metal, it accepts the lone pair electron. Okay. Now, so that is the meaning of central atom or ion. So that in coordination entity, the atom or ion to which a fixed number of ions or groups are bounded. To which one this fixed number of ions or groups are bonding, those that we call as central atom or ion. During the binding of those ions or groups or molecules to the central atom, they will approach to that central atom from any of its direction, right? So depending on the direction, geometry of that molecule depends. During that binding time, they may approach in any direction. Depending on the direction, geometry of that complex compound depends. Okay. So for example, if I take first one, cobalt. On this, when chlorine is going to bind with cobalt, it may approach like this. 3 chlorines may approach like this and 3 ammonia molecules approach like this, NH3, NH3 and NH3. Okay, so that here cobalt is going to approach around this, sorry, 3 chloride ions and 3 ammonia molecules are going to approach around the cobalt in this direction, which gives octahedral shape, Okay, so octahedral shape we can attain for this. Clear? So when that negative ions or neutral molecules or groups, when going to bind to the central metal atom, they should bind in specific directions so that it gives some specific geometry to the complex compound. Okay, right. Now we will see for which type of molecules which structure may possible. Okay, in this definitions only we see that. Now in this NiCl2H2O taken for, in this example, nickel is going to bind with 3 chloride ions and 4 water molecules. Since nickel is going to bind to 2 chlorines and 4 water molecules, nickel is the central metal atom. Okay, and in this complex compound, 5 ammonia molecules and 1 chlorine is going to bind with cobalt. So that cobalt is a central metal atom, and iron, in this 6 cyanide ions are going to bind with iron. So that iron is the central metal atom. To say simply, central atom is a transition metal. Okay, whatever the complex compound we are taking on that, which is transition metal, that belongs to central metal atom or ion. Sometimes that metal present as a neutral state, then we call that as central metal atom. In that complex compound, if that metal present in ionic state, then we call as central metal ion. That's why he mentioned either central metal atom or ion. Okay, for example, in these compounds, nickel present here as a +2, so that central metal ion, not atom. Here also CO +3, central metal ion, not atom. And here also Fe+3, central metal atom, not ion. But when do we say atom means? For example, if I take this NiCO taken 4 or NiCO taken 5, in this complex compound, nickel present in 0 state, so that nickel is the central atom, not central ion. Okay, central metal atom, not central metal ion. Okay to you? Right. So these are the 2 definitions of coordination compounds. What is coordination entity and what is what is central metal atom or ion? So coordination entity is the constituent of some fixed number of the ions or groups bounded to this central metal, that is bounded to the metal atom, right? And that metal atom we are calling as a central metal atom or ion. Okay, now the fixed number of ions or ligands which are going to bound to the central atom, those we call as ligands. For example, in this 6 cyanide negative ions are going to bind with iron, right? So since here 6 cyanide ions are going to bind with iron, these 6 cyanide ions we call as ligands. So these 6 cyanides we call as ligands. Those 6 we call as ligands. Okay, like that. Here also this 1 chlorine anion and 5 ammonia molecules. These also going to bind with cobalt, right? So these also we call as ligands. Okay. Now in this 4 water molecules and 2 chlorines are present. These 4 water molecules and 2 chlorines we call as collectively ligands. Here 4 water molecules and 2 chlorines we call as ligands. Okay. So here that number of ligands which are attached to the central metal atom in a coordination entity we call as coordination number. coordination number. For example, in this NiCO taken 4. Here 4 carbon monoxide neutral molecules are going to bind with nickel, right? So here this 4 CO we call as ligands, and nickel is the central metal atom. Okay, since how many ligands are going to bind to the nickel means 4 ligands. So that coordination number represented with Cn, coordination number is equal to 4. Coordination number is equal to 4. Now here 2 chlorines and 6 water molecules, they are going to bind with cobalt. So that here coordination number is 6, right? So here coordination number 6, and here can you say what is the coordination number? 1 chlorine and 5 ammonias are going to bind. So that coordination number 5, and in this 6 cyanides are going to bind. So that coordination number 6. Okay, and in this 3 chlorines and 3 ammonias are going to bind. So that coordination number 6. Okay, and here 2 chlorines and 2 ammonia molecules are going to bind. So that coordination number 4, and here 6 cyanides are going to bind. So that coordination number 6, and here 6 ammonia molecules are going to bind. So that coordination number 6, right? So the number of negative ions or neutral groups or neutral molecules going to bind to the central metal atom we call as coordination number. That negative ions or neutral molecules or groups we call as a ligands. So the number of ligands bounded to the central metal atom is called coordination number, right? Now, so let us come once about this structure. Okay, in this cobalt is binding to 6 ligands, right? Cobalt is binding to 6 ligands. If I remove those 6 ligands from the cobalt, if I remove the 6 ligands from the cobalt, okay, when we are going to remove the 6 ligands from the cobalt, these 6 ligands take their electrons which are given to cobalt. When we are going to remove these 6 ligands, then they will take their electrons. So when they are taking their electrons, then cobalt is going to get somewhat charge, positive charge, because electrons are going away from the cobalt. So that cobalt will get some charge. That charge gained by the central metal atom or ion when all the ligands are removed from it along with their bond pair electrons is called oxidation number of that central metal atom. We call it as oxidation number of that central metal atom. Okay, since I told that each and every central metal atom has a fixed number of ligands, means coordination number as constant, its oxidation number also constant. Oxidation number for any metal is a constant, okay, but that depends on which type of ligands are going to bind, negative ligands or positive ligands or neutral ligands. Okay, right. So here what is oxidation number we discussed, and what is coordination number we discussed. Okay, depending on the coordination number, those ligands how they are arranging in the spatial orientation around the central metal atom depends. Depending on this coordination number means depending on the number of ligands, those ligands how they are arranging around the central metal atom, and which direction they arrange, that depends on number of the ligands or coordination number. That spatial orientation of the ligands around the central atom we call as coordination polyhedron. We call it as coordination polyhedron. Okay, so let us see what is that coordination polyhedron possible for different complex compounds means for which coordination number, which coordination polyhedron come. Okay, so let us see that once. Okay, so here if you say for coordination number 6, if you take for coordination number 6, if I taking coordination number 6, 6 ligands are there. So those 6 ligands may arrange in octahedral manner. Okay, and if I take coordination number 4, if coordination number 4 is there, means if the ligands around the central metal atoms are 4, then it may arrange either tetrahedral or square planar. To give the square planar structure, that central metal atom should participate in dsp2 hybridization. To give this tetrahedral structure, that central metal atom should participate in sp3 hybridization. Okay, and to give octahedral shape, that central metal atom may participate either d2 sp3 or sp3 d2 hybridization. We will discuss what hybridization possible in later videos. Okay, so here depending on the hybridization given by the central metal atom with the coordination number 4, shape of the molecule depends. Okay, like that, if coordination number is 5, if coordination number is 5 means 5 ligands, 1, 2, 3, 4, 5, right? Here also 1, 2, 3, 4, 5. So if coordination number is 5 means 5 ligands are present, then they may arrange either in the trigonal bipyramid or square planar structure. So which one possible means that depends on the hybridization. If sp3d hybridization is there, then it gives trigonal bipyramid shape, and if dsp3 hybridization is there, then it gives square pyramid structure. Okay, so depending on the coordination number, whether coordination number 5 or 6 or 3 or 2 or 1 or 4, so depending on that coordination number, geometry of the complex compound depends. That spatial orientation of the ligands when they are going to bind with central metal atom, we are calling as coordination polyhedron, right? Now, so here for example, if I take CONH3 taken 6, in this coordination number is 6. Coordination number 6. So coordination number 6 means it should give octahedral shape. Here coordination number 4. Coordination number 4 means may possible either tetrahedral or square planar. That depends on the hybridization of the central metal atom, right? So here this compound give tetrahedral shape, but this also coordination number 4. Coordination number 4, but it is giving square planar. Means in this platinum participate in dsp2 hybridization, but in this nickel participate in sp3 hybridization, right? So depending on the hybridization, even the coordination number is same, shape changes. Okay, right. Now we already discussed about what is the oxidation number of the central atom. Means the charge carried by the central metal atom if all the ligands are removed electron with their electron that are shared with the central atom. When ligands are going to bind with the central atom, they are giving or they are sharing their electron to the metal atom. So when we are removing their ligands, those shared pair electrons also we are removing. So then central metal atom gains some charge. The charge we call as oxidation number or oxidation state of central metal atom or ion. Okay. Now that oxidation number generally we have to represent by a Roman numerical number in parenthesis following the name of the coordination entity or metal name. For example, if I take in a compound, in this copper is going to form +1 oxidation state. Okay, so that oxidation number is +1. That number we have to represent in Roman number, right? So Roman number means +1 we have to represent as a 1. That we should keep in parenthesis, means in bracket. Okay, so in bracket we have to keep that +1 in Roman number, so that 1 followed by, that is that Roman number oxidation state should followed by the metal name. That means Cu1. Okay. For example, in a compound, if iron is going to form +3 state, then how we have to write down that oxidation state means iron 3. How do we write down means cobalt +2 means cobalt 2. Right. So that oxidation state we should write in Roman number in parenthesis. Okay. Before that we have to write down the metal symbol or metal name. Okay to you? Right. So this is about oxidation number. And if a complex compound contains same type of ligands, there are no other ligands, then we call that as homoleptic. Homo means same, hetero means different. If same type of ligands are present, then we call that as homoleptic complex compound. If different type of ligands are present, then we call that as heteroleptic complex compound, right? So here CONH3 taken for Cl2. In this 4 ammonia ligands and 2 chloride ligands, different type. Ammonia is one type of species and chlorine another type of species. So that different type of ligands are present. So that heterolytic compound, complex compound. But in this 6 ammonia molecules are of same type. There is no other ligand, right? So that homoleptic complex compound. Okay, can you say which type of ligand it is? Sorry, which type of complex compound it is? For example, I am writing this PtCl4-2. Is it homoleptic or heteroleptic? Yes, homoleptic, because 4 chlorines are present which are same type, right? And this compounds also, which one? COCN taken 4-3. It is also homoleptic, right? So do you have idea? Clear idea about the homoleptic and heteroleptic and oxidation number? Yes? Okay, right. Now let us go to another one. What is that means? Coordination number we already discussed. Coordination number is nothing but the number of ligands donor atoms to which the number of ligand donor atoms. The number of ligand donor atoms which are bonded to the metal is called directly bonded is called coordination number. Let us see what is the meaning of this number of ligand donor atoms, not the number of donor atoms. Sometimes we can take as the number of ligands, but sometimes it not follow that rule. So that we have to give exact definition as the number of ligand donor atoms. Okay. For example, if I take first example PtCl6, on that platinum is going to bind with 6 chlorine ligands, means 6 Cl minus in octahedral manner. So that coordination number is 6. In this only one chlorine is there, that one chlorine is giving electron density, that is lone pair electron to the platinum, right? So only one donor atom is there, that is Cl. But if I take C2O4, the structure of C2O4 is C double bond O. The structure of C2O is C double bond O, C double bond O minus, O minus. It is a negative ligand. Okay. This one, this oxygen gives its electron density, that is lone pair electrons to the metal, and this oxygen also give lone pair electron to metal. Is it clear? So this oxygen give lone pair electron to the metal, and this oxygen also give lone pair electron to metal. Clear? Now here this is one ligand only, right? One ligand only. Ligand number is 1, but on that how many donor atoms are there? 2 donor atoms, 2 oxygens acting as a donor. So the 2 donor atoms are present. Okay. Since here 2 donor atoms are present, we call this as bidentate ligand. Bidentate ligand. Bidentate ligand is a ligand where 2 donor atoms are present. Okay. But if I take here only one chlorine is donating lone pair electron. So this chlorine we call as monodentate ligand. The dentate indicates number of lone pair electrons donating. If one lone pair electron donating, monodentate. Two lone pair electron donating, bidentate ligand. Okay. If more than two are donating, then we call that as polydentate ligand. Polydentate ligand. For example, if I take EDTA, that is EN tries, ethylenediamine, this structure is NH2, CH2, CH2, NH2. This is the structure of EN, ethylenediamine, or one ethane 1,2 diamine. Okay, ethane 1,2 diamine. That is the IUPAC name, but common name is ethylenediamine. CH2 CH2 is nothing but ethylene. Two amine groups are there, so that ethylenediamine. In this ethylenediamine, this nitrogen give lone pair electron to the metal atom, and this nitrogen also give lone pair electron to metal atom, so that both donor atoms are present on the same ligand, right? This entire one is one ligand, on that two donor atoms are there. So that this is also an example for bidentate ligand. Bidentate ligand. Bidentate ligand. Okay, is it clear? So monodentate ligand, bidentate ligand. Okay, like that, if I take ADTA, that acts as a polydentate ligand, means hexadentate ligand, we will see. Okay, but here, is it clear now? Right, now if we take coordination sphere, what is coordination sphere means? It is same like that of coordination entity. What is coordination entity? The constituent of fixed number of ions or groups which are bounded to the central metal atom. That constituent together we call as a coordination entity. That coordination entity we are also calling as coordination sphere. Okay, so coordination sphere is the central atom and the ligands attached to it are enclosed in the square bracket and collectively termed as the coordination sphere. In coordination entity means ligands and central metal atom, those only we are taking. Okay, square bracket we are not considering, right? If you are including the square bracket also, then we call that as coordination sphere. Okay, so that's why he is saying collectively enclosed in square bracket. In coordination entity, the constituents of the ions or groups which are bonded to the metal atom, that's all. They are not enclosed in the square bracket, but here enclosed in the square bracket. Okay, but in general, since depending on that number of ions and central metal atom, depends on that central metal atom and number of ligands attached to it, complex compound geometry and everything depends. So that in general coordination entity and coordination sphere we call as same. Coordination sphere and coordination entity we call as same, but only difference is if you are not taking the square bracket, coordination entity. If you are including the square bracket, coordination sphere. Okay, so whatever we are writing outside the square bracket in complex compound, that we call as counter ions. We call that as counter ions. Those counter ions only completely ionize, but coordination sphere not completely ionize. That entire one give as a one ion. Okay, so that if I am taking this complex compound, here 4 potassiums are there outside the square bracket, those completely ionize to give 4K plus. That K plus we call as a counter ion. And what is the coordination sphere here means? Which one is keeping inside the square bracket? That entire square bracket is coordination sphere. That entire square bracket is coordination sphere. Okay? Is it clear? Right. Okay to you? So that we discussed about coordination number and coordination sphere, counter ions, how do you distinguish and which one completely ionizable, which one not completely ionizable. Okay, and we discussed about oxidation number, that is coordination polyhedron, and oxidation number, homoleptic complexes, heteroleptic complexes, right? Now, let us see about different types of ligands. This we discussed. What is the ligand? Ligand is nothing but an ion or molecule which is going to bind to the central metal atom, right? Some fixed number of ions or groups which are going to bind to the central atom we call as ligand. Okay, now that ligand may be simple ions like OHCl minus, that is hydroxide or chloride or ammonia molecules like that, or small molecules, neutral molecules, or maybe large molecules, means molecular weight is more, or a macromolecules like proteins or biomolecules. Okay, these also acts as a ligands. But in this, depending on how many atoms are going to donate lone pair electron to the metal atom, depending on that, we can classify the ligands as unidentate, bidentate, we discussed. Unidentate means only one donor atom is present on that, means only one donor atom is going to bind to central metal atom, right? Okay, so these are the few examples of single donor atoms, means unidentate ligand. In this, chlorine donating, in this oxygen 2 lone pair electrons are there, but only one lone pair electron is donating. Ammonia, nitrogen has one lone pair electron. Since only one lone pair electrons are donating, we call this as unidentate ligand. But in this, just now we discussed NH2CH2, CH2, NH2, EN, ethylene in this ethylene diamine, this nitrogen and this nitrogen, two donor atoms are present. Those two donate lone pair electron to metal atom. So that bidentate ligand. In C2O4 minus 2 also, it is structure C double bond O, C double bond O, O minus, O minus. So here this oxygen has a chance to donate and this oxygen also has a chance to donate. So that bidentate ligand. Okay. Now, if you see another type of ligand, that is polydentate ligand, means if more than two donor atoms are present, if more than two donor atoms are present, then we call that as polydentate ligand. The best example of polydentate ligand is EDTA. This is the structure of EDTA. In this oxygen donate lone pair electron to the metal. This oxygen also donate lone pair electron. This oxygen also donate lone pair electron. This oxygen also donate lone pair electron. And here nitrogen also has one lone pair electron. That also donate lone pair electron. So that how many donor atoms are present in this EDTA? 6. 4 oxygen atoms and 2 nitrogen atoms. That's why it is called hexadentate ligand. 6 donor atoms are there, means greater than 2 donor atoms. So that polydentate ligand, and that it belongs to hexadentate ligand. Hexadentate ligand. Okay. Now, when this polydentate ligand or bidentate ligand, for example, I am taking C double bond O, C double bond O, O minus, O minus, means oxalato ion. This oxalato ion, when going to bind to the central metal atom, it forms a ring, right? It forms a ring-like structure with the metal atom, right? Okay. And here also, when it is going to bind, EDTA is going to bind to the central metal atom, then it is forming a ring between these. And here also, it is going to form a ring here, right? So, since they are forming a ring during their binding time, we call those ligands as chelate ligands. Chelate ligands are the ligands which are bounded to the central metal atom and forms a ring-like structure. Okay? So, when these chelate ligands are forming a ring-like structure, those complex compounds are getting more stable than non-chelate ligands. Okay? These chelate ligands give more stability to the complex compounds than non-chelate ligands. For example, if I take CO, C2O4, CO2O4 taken twice minus 3 this ligand complex compound I am taking, and COH2O taken 6 plus 3 complex compound I am taking. Both are cobalt complex compound. But in this ligand is oxalato-bidentate ligand. In this ligand is water monodentate ligand, right? Okay. In this water is a monodentate ligand. In this oxalato is a bidentate ligand. And this bidentate ligand is a chelate ligand, but it is a non-chelate ligand. There is no ring formation by the water molecule. So due to formation of this ring structure by the C2O4 like this, it gives more stability to that complex compound than that water complex compound. That's why between these two, this one is more stable, this one unstable. This one unstable complex compound. Okay. So these are the definitions we have to learn about this coordination compounds. So what are those definitions we discussed here means coordination entity, coordination sphere, coordination number, coordination the polyhedron, oxidation number, homolytic, that is homoleptic complex, heteroleptic complex, and different types of the ligands, monodentate ligand, bidentate ligand, polydentate ligand, chelate ligand. Okay, and one more type of ligand is there, that is ambidentate ligand. What is that ambidentate ligand means? In monodentate ligand, most of the di and polydentate ligand they act as a chelate ligand by forming a ring-like structure with the metal atom, right? Polydentate and didentate ligand. If I take monodentate ligand, in sometimes monodentate ligand, this NO2 minus we call as nitrito ligand. It is a monodentate. This SCN minus we call as thiocyaneto. It is also a monodentate ligand because when NO2, that is actual structure of NO2 is this one, N double bond O minus. In this oxygen has two lone pair electron, and this oxygen has also two lone pair electrons. This nitrogen has one lone pair electron. During the binding of this NO2 to the metal atom, this nitrogen may bind to the metal atom, gives this complex compound, or this oxygen may has a chance to bind to metal atom, then give this structure. Okay, negatively charged oxygen may has a chance to bind to metal, but on that when it is going to bind, it give one lone pair electron to the metal, right? So this oxygen, one lone pair electron is giving to oxygen. Since only one donor atom is giving monodentate ligand, here also one donor atom is giving. Okay, at a time they are not giving two time, that is nitrogen and oxygen, at a time they are not giving. Any one of that atom giving to metal atom, that's the only monodentate ligand. Clear? But since both the atoms has a chance to donate the electron pair, we call that as ambidentate ligand. Okay? In a ligand, if two different donor atoms are present to donate to the metal atom, such type of ligands we call as ambidentate ligand. Okay? Now, if I take SCN minus, that is cyanide, in that SCN minus, nitrogen has lone pair electron and sulfur also has lone pair electron. This cyanide has a chance to bind to the metal, or nitrogen also has a chance to bind to metal. Okay, if sulfur is binding, then we call that as thiocyaneto, yes, means sulfur binding, and nitrogen binding means thiocyaneto, N. Okay, depending on this name, we can say which atom of that SCN minus binding to the metal. Okay, like that. Another example of ambidentate ligand is Cn minus. In this Cn minus, nitrogen may bind to the metal atom, or carbon may bind to the metal atom. If carbon bind to the metal atom means cyano complex compound. If nitrogen bind to the metal atom means isocyano complex compound. Okay, so these are the definitions we have to learn to know the coordination compounds. Okay, so based on this, let us see one question what we discussed here. Specify the oxidation number, coordination number and geometry of the complex compound. Okay, so coordination number means here one water molecule and one cyanide, 2 En, right? But this En is a bidentate ligand. 1 En, 2 donor atoms are there. 2 En means here 4 donor atoms, right? And here 1 donor atom and here 1 donor atom. So collectively gives 6. So that coordination number for this one is 6, right? And oxidation number is plus 3. Okay, that we have to calculate based on the charge of the ligand. That we will see after nomenclature. Okay, right. Now, if you are taking here 2 bromines and En means bidentate, 2 are there, means 4 donor atoms are present. 4 donors and here 2 donors. So that coordination number for this cobalt is 6 and oxidation state is plus 3. I told oxidation number for any metal in a specific metal in a complex compound is always constant. It never change. Here plus 3, here also plus 3. Okay. And in this complex compound, if I take 4 chlorines are binding and chlorine is a monodentate ligand. So that 4 donor atoms are there around the platinum. So that coordination number is 6. Right. And in this oxidation state is plus 2. Okay. And in this 3 ammonias and 3 chlorines are binding. So that coordination number is 6. Okay. And chromium oxidation state is plus 3. Clear? And in this iron, you can say that 6 cyanides are binding and 3 potassiums are binding. But here 3 potassiums are present outside the square bracket or inside the square bracket? Outside. Outside means counter ions that won't directly bound to the central metal atom. The ligands which are kept inside the square bracket only directly bound to metal atom. So that here iron, since binding to 6 cyanide monodentate ligands, coordination number is 6. Potassiums are not binding directly to the central metal atom. And here oxidation state for this iron is plus 3. Okay. Now since here coordination number is 6, then geometry for this one is octahedral. And here also coordination number 6, so that octahedral. And coordination number here also 6, so that octahedral. And here also coordination number 6 means octahedral. And here coordination number 4. Coordination number 4. So coordination number 4 means maybe tetrahedral or square planar, right? But here platinum is a 5D element. So for 6D and 5D elements, square planar complex compounds possible. Means square planar geometry possible. Okay. So that geometry for this one is square planar, and for this octahedral, and for this octahedral, and for this octahedral, and this also octahedral. Okay. So like this we can give any answer to any question if you ask. Okay. Is it clear to you all? Right. So hope you like this video, and if you like this video, please try to share, comment, and so that I will try to improve my mistakes on this video. Okay. So all the best for you.